we've come to the end of the presentations of the workshop, and I have the singular honor of displaying all the simulation and visualization contest winners. This is something I like to do every year. And because I'm doing this, you guys have to look at my visualizations, even though I didn't enter them into the contest. This is all one I did of a steel project I was working on a long time ago.
So is this mesh that's kind of added?
Yeah, it's
on top of a picture.
Yeah, I use this is marketing. Right, that isn't actually the mesh. It's a pretty coarse mesh for that problem. So every year we hold this contest for sort of the most interesting simulations and visualizations. We continue to get lots of good entries. So again, we've broken it into two categories: still images and animations. We'll probably keep doing that every year because you guys keep making awesome stills and animations. We judge these sort of, partially on aesthetic qualities, but also sort of on the novelty of approaches or, interesting, cool whiz-bang factor and any kind of notability of application. So if it looked like it was really hard to put together, that definitely factored in. And so the result of all these good visualizations that came out of this will land on our webpage. And the winners receive M&M t-shirts. You're still good for that, right, Sonia?
Yeah, the winners for sure.
Yeah.
Maybe even some of the runner-ups.
Oh, you heard it. All right, so I'm going to go ahead. So the runner-up for still images. This is a really interesting one. And you guys saw this earlier. So this is the Penrose unilluminable room appears rather illuminable in 3D. It's a solution to the Helmholtz equation computed using the Wave-Holtz iterative algorithm with the symmetric interior penalty DG discretization accelerated on GPU by Amit Roshan at Virginia Tech. Amit, you want to chime in and say a couple words?
Sure, yeah. So yeah, I talked about this a bit earlier, but kind of this problem was interesting for my research because I work on this Wave-Holtz algorithm. And so what was nice about putting it in MFEM and using the new interior penalty DG method is that I was actually able to produce this solution much faster than the ways that I was doing it previously. Before that, I couldn't even really do a high frequency problem in 3D, just the 2D ones. So it was nice to use MFEM for this.
Very cool. How did you generate that mesh? It's obviously an interesting shape, right?
Yeah, so I had one in 2D that was just taking the curves are all ellipses, so there's kind of a nice way to do that in Gmesh, and then I just rotated the mesh and added a column in the center to fill in the gaps, so it wouldn't generate any wedge elements, just quads and hexes.
Nice, and it's a high order mesh, so you get the curves.
Yes, all the elements are second order, I think.
Yeah, high order for the land. Well, thanks, Amit. This is excellent.
What was the image made with? Was it?
Oh, this is with ParaView.
ParaView. Okay.
Well, I do want to add something. Amit is a PhD. You're a PhD student, correct, Amit?
Yeah.
Yeah. So you don't even have to be a postdoc.
Yeah.
To be in the right. Just say.
Yes.
All right.
Well, let's give Amit another round of applause, please. Oh, good. My laptop is rough. Okay, so the winner for still images is a displacement distribution of a loaded excavator arm under static equilibrium using MFEM. A library has been developed for simulating deformable articulated mechanical assemblies consisting of elastic bodies interconnected via various joint types. So this was this is really cool to see an assemblage put together from multiple meshes using MFEM. So, Miran, congratulations.
Thank you very much.
Do you want to say a few words about this?
Sure. So I'm part of Autodesk Research, and about a few months ago, we started thinking about developing a final element solver for mechanical assemblies under static loading and dynamic loading. We started from static loading, and then we considered different final element libraries out there. Some of them you mentioned in this workshop. And we ended up going with MFEM because of the flexibilities and the capabilities it has, both in terms of the integrators and also the linear, the solvers it provides for solving the linear or nonlinear equations. And so what you see in here is one of the first examples we created using that library we created on top of MFEM. It's called Elementum. So you're probably, if we open source it, you're gonna hear about it in the future. But
that was going to be my first question. Is it open source?
It's still internal. We are gonna add capabilities to it. So again, it's been only 6 months we started working on it, but hopefully the purpose is in the future we're gonna add more capabilities in terms of solid mechanical capabilities, like for dynamic simulations or some other things that we need in our team, and then hopefully we open source it.
Yeah, this is really interesting, Mehran. That we'll be, if you guys are interested in collaboration or talking, we'll definitely.
Absolutely. We were just looking for an avenue to start the collaboration, and there's a lot of areas that we can work together, and we would love to get in touch with you guys.
Look, I have a short question maybe to clarify. So in here you're saying assemblies. Does that imply that like each part has its own mesh, and then there is some coupling, like
exactly
things and like that?
Yeah. So each part has its own mesh, and then we define, depending on how the components are connected together, we have different joint types. Like for this example, we have like revolute joints, some spherical joints. We have like different kind of joint types, and then we just define add constraints, like we form those equations in terms of some constraint equations, and so we end up having a saddle point system, and then we solve that saddle point system through a projected conjugate gradient that we developed using MFEM API, and then we solve it. Yeah.
Okay.
Cool. Is there any chance this code's going to end up in any of your CAD products, or?
Maybe. It really depends. That's not the original goal. So because we are part of research, our goal is mostly writing papers. But if there's enough interest in the other parts of our organization, there has been precedence before that these codes will be integrated into or as a whole or part of the code into a product eventually. But we don't know as of yet.
Sure. Will you let us know if that happens? Because we'll want to know about that.
Let me just also say we do these workshops every year, so maybe next year you can actually tell us more about it in a talk.
Sure. Yeah, I would love to.
And next year, I think the this ARM is going to be passé. I think you're going to have to go to a full-fledged mechatronic robot.
Actually, that's the goal. That's the goal.
Blocking. I think you're shooing.
Yeah. Eventually, we want to be able to have a multi-body dynamic solver.
Mm-hmm. Yeah.
So.
Yeah. That'd be awesome.
Very cool.
Very cool. Very cool. All right. Any more questions for Miran?
I want to be in touch with the team behind our team, not just me. We have good researchers in our team too. So I don't know what is the starting point of this connection and how we can get in touch. I would love to be able to start that.
I think we'll arrange a meeting and so we can introduce the teams to each other.
Absolutely.
I'll have to get in touch because I have to ship you a t-shirt. But I'll send you a message on Slack. Are you on Slack?
I am,
Yeah.
yes, you're a Slack. And I hope you have my email too. So if I didn't,
Yes.
I will try
We'll
to.
reach out. We'll reach out.
Okay, sounds good. I'll wait for that. Thank you.
Excellent. Let's give Moran another round of applause. All right. So, like I said, this year we had a lot of. Oh, wait. I almost forgot to do the animations. Okay, so on to the animations. So the runner-up for animations is a shock bubble interaction utilizing a property-preserving discontinuous Galerkin scheme. Okay, so now what I'm going to have to do, this is not embedded, so I have to pop out and launch this thing here. You guys see this?
No.
No. Give me a sec. Okay. Sorry, the embedding is pretty bad. There we go.
You're just sharing PowerPoint, right?
Yeah, that's the way to go. Stop. Use the Zoom. Let me do full screen. Okay.
Yes.
You see
Well,
that?
no.
Okay, and now you see that.
Yes. Yes.
All right, I'm gonna play this thing. Sorry, guys. I'm just amazed at how far this thing runs. Excellent.
Yeah, play it again.
I'm gonna play it one more time, and then we'll go ahead. Bring you in to talk about this.
Is that grunge or not?
I will ask that question. I would be surprised if that's full grunge.
All right.
Okay, so Hannes, let's give Hannes a round of applause. Hannes, you want to say a few words about this?
Yeah, thank you very much. Can you hear me?
Yeah.
Perfect. Yeah, thanks for nominating me here. So maybe I can just use this platform to advertise a bit. My former advisor and I have a book published, and we needed a cover. And so, this simulation is where the cover was taken from. It's using a property preserving DG scheme, high resolution, obviously, and it's showing both shock capturing, positivity preservation, and also the vortices. And Will Passner has similar methods, it's just to make a cool animation and not really anything else.
Makes a really good book cover. I actually took a look at it earlier.
Okay. Yeah.
So there were a couple of questions. I saw one go by. What was the resolution of the mesh on this thing?
So it's I can look it up. It's more than 1 million elements, and it's Q1 discretization.
Q1. And was it Lagrangian or Eulerian?
This was Eulerian.
That was my guess. Yeah.
Yeah.
Well, very cool. Any other questions?
It's the furthest that I've seen this particular problem being run. So that's pretty cool.
What's that, Sanyo?
It's the furthest that I've seen this particular problem being run. So
I mean, there's these benchmarks from Remy Abgral and from the 90s and such, but I modified it. It's like the reflecting boundaries. They have cool features with like the shock reflections and stuff, and so it's less about physics and about images, I guess.
It's fun.
bonus points for using GeoVis.
Yeah, always.
I mean, I the things I love most about MFM is GeoVis, honestly. So yeah.
Forget the rest of the stuff.
Wow. Okay.
Okay, thanks, guys.
Yeah, well, let's give Hannes another round of applause. Okay, and finally, the moment we've all been waiting for. The winner of animations goes to John Camier for leapfrogging vortex rings based on an MFEM incompressible Schrodinger fluid solver, which captures thin vortex dynamics without advection and nonlinear terms. This thing is rad looking. Give me a second on this. I'm gonna open it up. Like mesmerizing.
It's a little choppy
It is,
here. But
yeah.
It's actually smoother if you're.
It's smoother on my screen, unfortunately.
It is pretty cool.
Yeah.
Does anybody know if this is a real phenomenon?
Well,
Does this actually happen in nature?
we're gonna have to ask John, I think. So let's give John a round of applause.
If
Do you want to tell us a little bit about this?
Yeah, sure. But it's something that I had in mind. Wanted to do some fluid solver, but needed something that was kind of easier. So that's why I found this kind of simple with non-linear advection terms, while capturing all these vorticities. So yeah, the main trick is that we need several DOFs per DOFs. It's each DOF can be seen as a quaternion. It's GPU friendly. I only needed a mass diffusion gradient and a Poisson solver to produce this. And the rendering was made through Blender, though.
Yeah.
We'll forgive you for using Blender. It looks awesome.
No.
Any questions for John?
But some simulation was running FM code, like you mentioned.
Yeah.
Years.
Yeah, it was on the GPU. It's 2 million DOFs and 64,000 particles.
You did it on one GPU?
Yeah, that's right.
Nice.
Uh,
That's really cool. What's I'm not familiar with the Schrodinger fluid equation. Is there a particular physical phenomenon that models?
Well, it's more a way to transpose from the Schrodinger equation to fluid solver. So it's like a 100-year-old paper, the Mablin transform that gives this transposition possible. So there's a way from this wave functions to go back and forth to fluid density and the velocities.
Very cool. Well, it makes some awesome rings for sure.
Yeah.
so is the domain like a box here, and this is just like a surface of something?
You're right. For now, it's just a regular box, 128 cube for this run.
So you have what fields are being solved for, and what's actually being visualized here.
So there's two wave functions, two complex wave functions at each H1 DOFs. And there's velocities on the edge, on the ND FE FEC. And there's particles that are animated through this or advected through these velocities.
Mm-hmm. And what's the visualization based on? Is it from the velocity field, or is it?
That's right. Yeah,
particles?
correct. The particles.
Very, very cool.
It looks like there's a lot of detail. I almost want to see. This is super cool, but I want to see it kind of on the black background so I can just stare at the detail. It's John. Do you happen to know? Is this a real phenomenon? Does this happen in nature?
Yeah. But there's this. There's movies of a long time ago where people just do these vortices and
Wow.
Yeah.
It somehow feels that it shouldn't happen, but I guess there's this. Yeah. Wow. Amazing stuff.
And now I'm going to be on YouTube tonight looking for
This is
videos.
super impressive. This one by
Yeah.
there was no discussion.
You know,
Yeah, we all want to. We all want to.
Thank you.
All right, so that's it for the winners. But I wanted to mention everyone else. These are a bunch of pictures from the other ones. There was a lot of really good entries this year, and it definitely made it hard to choose. There was multiple shape optimization ones. There was some really cool wave phenomenon going on, and obviously some great CFD work. As well. So all these great images and videos, they'll definitely end up on the MFed webpage. And thank you all for entering the contest, even if you didn't get away with a t-shirt. But please try again next year. Okay, so there's a few more things I just wanted to wrap up. Just go through a few resources and thank everybody. So I just wanted to flash this up one last time. We got a lot of resources. I know some of you are new, so make sure you check out our repo or our webpage. The issues on our repo and our group on our repo are two ways to give us feedback and contact us and talk with us. Obviously, on the mfem.org website, you can always find information about this workshop and future workshops. On that page, we have a publications page where you can keep track of the publications that we've put out and others that I believe we have some that others in the community have put out there too. Mm-hmm. And then you can keep contacting us on the MFEM workshop Slack as well. And yeah, if you run into trouble, there's always GitHub issues. So we'll definitely see you next year. We plan to do this again, and maybe we'll have a hybrid option next year. So at the end, we're at the end of the workshop. So I'd like to give applause for all the speakers, please. And some special thanks to the planning committee, Zania, Will, Socrates, Caden, Milan, Vladimir, and of course, Holly, who refuses to put herself on the front page with all of us, but was always in the background making this event better. So round of applause for them as well, please.